A company has to design a rectangular box for a new range of jelly beans. The box is to be assembled from a single piece of cardboard, cut from a rectangular sheet measuring 31 centimeters by 22 centimeters. The box is to have a capacity or volume of 500 centimeters cubed. The net for the box is shown below. The company is going to use the full length and width of the rectangular piece of cardboard. The shaded areas are flaps of width 1 centimeter, which are needed for assembly. The height of the box is h centimeters, as shown on the diagram. Write the dimensions of the box in centimeters in terms of h. Here I've marked in the widths of the flaps. Also, this distance is h, same as this. These two sides are the same. And these two sides here are the same. So this distance here has to be h. This is the bit that fits on top of the box. So now let's get this distance here in terms of h. Well, the distance from here to here is 22. So we want to subtract from 22 h plus 1 plus another h plus another 1. So here we have it. We have 22 minus h minus h minus 1 minus 1. That's going to give us 20 minus 2h. 22 minus 2 is 20. So I can write in here 20 minus 2h. Now let's consider this distance here, which I call x. It's actually the same as one side of the top of the box. Of course, we know what this side is. This is the same as this. It's 20 minus 2h. So, how do we find x? Well, we see that 1, this distance here, plus x plus h plus another x plus another h must equal 31. So, rearranging this, we have two x's on the left hand side. We have two h's plus 1. So we bring over the 2h and bring over the 1. So we get 2x equals 30 minus 2h, which means that x equals this divided by 2. If we divide this expression by 2, we get 15 minus 1h for x. So we can check this by adding up these lengths. H plus 15 minus h is 15. 15 plus h, and we've 15 minus h. That gives us 30. 30 plus 1 equals 31. So now if we assemble this box, we have the three sides of it. So one side of the top has length 15 minus h, the same as one side of the bottom. So this side here. And the other side, this distance here, is 20 minus 2h. And we have the height of the box h. So we need just three dimensions to specify this box. And we know that its volume is 500. So to get the volume of a box, we just multiply the three sides together. Anyway, before we do that, I'm going to fill in these values. Now, it doesn't matter which of these is the length and which is the width. It makes no difference really for a box. So here's the expression for the capacity or volume of the box in terms of h. Show that the value of h that gives a box with a square bottom will give the correct capacity. Well, if the bottom is square, then we must have that 15 minus h equals 20 minus 2h. So, what value of h satisfies this condition? Bring the h's to one side. 2h minus h is h. 20 minus 15 is 5. Let's plug 5 into this equation and see if it satisfies this equation. Well, we have 20 minus 2 times 5, that's 20 minus 10. And we have 15 minus 5, which is 10. And we have a 5 here. 20 minus 10 is 10. So we have 10 times 10 times 5. 10 times 100. 100 times 5 is 500. So indeed, this is a solution of this equation here. Find correct to one decimal place the other value of h that gives a box of the correct capacity. Well, here's the equation. We know that h equals 5 is a solution. Now this is actually a cubic equation. Let's get into the standard form of a cubic equation. That means we need to have 0 on the right hand side. To simplify the multiplication here, we can divide across by 2. So we have 10 minus h times 15 minus h times h equals 500 divided by 2. Let's multiply this out. So minus h by minus h is plus h squared. We have a minus 10 minus 15 h, which is minus 25h, and we've 10 times 15 is 150. And this, of course, is multiplied by h. That gives us 250, and we get h cubed minus 25h squared plus 150h minus 250 equals 0. Now, we know from the factor theorem that if h equals 5 is a solution of the equation f of h equals 0, where f of h is this expression here, then h minus 5 is a factor of f of h. So we had to get it in our equation into this form. We had to get 0 on the right hand side to apply the factor theorem. So now we can solve this equation to find other values of h. So we take h minus 5 and divide it into f of h. So h into h cubed goes h squared times, multiplying we get back to h cubed, get minus 5h squared, subtracting we get minus 25 plus 5 is minus 20. Take down the next term. Divide again. So minus 20 by h is minus 20h squared, we get that back. Minus 20 by minus 5 is plus 100. Next step is to subtract. So here we get 50h. Dividing h into 50h gives us 50. Actually, I forgot to take down. Divide, multiply, subtract, take down this term, minus 250. Divide again, gives 50 here. Now we must end up with a remainder of 0. 50 times h minus 5 is 50h minus 250. And if we subtract these, we do indeed get 0. Now that's important because by the factor theorem, h minus 5 is a factor of this. So it divides into it and leaves no remainder. This means if we multiply h minus 5 by h squared minus 20h plus 50, we'll get f of h, this cubic. So now we know we can write f of h like this as the product of these two factors. And we want to solve the equation f of h equals 0. So we have a product equaling 0, so we know what to do here. We put each factor equal to 0. We get back this one as we saw before. So now we have to solve this quadratic equation. I don't think this has factors, so we'll use the formula. So h is minus b plus or minus the square root of b squared minus 4 times a times c divided by 2a. We get the values 2.92 or 17.07. So here are the three solutions to the cubic equation. We know that since the equation is cubic, we have at most three distinct solutions. However, this solution here is not valid. The reason why is that if we plug 17.07 in here to get the length and width corresponding to it, we get negative values for each of these. 20 minus 2 times 17.07 is negative, and that makes no sense. Both the length and the width have to be positive. 15 minus 17.07 is also negative. Of course, lengths have to be positive, so we can forget about this one. It's not a valid solution. It solves the cubic equation, but it doesn't solve the physical problem. However, if h equals 2.92, we don't have a problem. If we plug 2.92 in for h, we get something positive, and similarly, the width will come out to be positive. So there are two solutions, h equals 5 or h equals 292, that solve the physical problem. The client is planning a special 10% extra free promotion and needs to increase the capacity of the box by 10%. So to increase the volume of the box by 10%, we get 110% of 500. So we multiply 1.1 by 500. That's 550. The company is checking whether they can make this new box from a piece of cardboard the same size as the original one, which was 31 by 22. A graph of the box's capacity as a function of h is shown below. Use the graph to explain why it is not possible to make the larger box from such a piece of cardboard. So this is the graph of 15 minus h times 20 minus 2h times h, where the sides of the box are h, 15 minus h, and 20 minus 2h. So we just multiply the three sides together to get the volume. If the volume is 550, we get a value of h that is between 17 and 18. So we see that f of 17 point something is 550. The problem with a value of h like 17 point something is that it makes two of the sides have negative lengths. 15 minus 17 will be negative. And 20 minus 2 times 17 will also be negative. And of course we don't want that. These values have to be positive. All of these have to be positive. So it's not possible to construct a box with a value of h between 17 and 18.